Alright guys, let's review experiment 3, Fischer esterification multi-outcome experiment. We're going to use acetic acid and ethanol as example to show you how the reaction proceeds, and you want to refresh your memory on mechanisms and also the spectra involved. Okay. Alright, first let's provide the balance equation for this reaction. Did I balance it? No, I have 3 oxygens on the left and I should have 3 oxygens on the right, right? What's missing? Well, we know that in the Fischer esterification reaction, you're creating an ester, and acetic acid will provide OH while ethanol will provide hydrogen to form water byproduct, right? And now it's a balanced equation. Except the reaction happened in either conventional heating or microwave heating. You need to give it a little heat to push it. At the same time, sulfuric acid was used as the catalyst to catalyze the reaction. And now we have a balanced equation. Second question. Since it's an equilibrium reaction, if I want a reaction to go to the right, if I want to push it forward to form the ester, what should I do? Well, the reaction will only happen or occur under heat. So heating is one of the ways, right? I can either use sulfuric acid or other catalyst to help push the reaction to the right, right? Would sodium hydroxide work? Nope. That's actually the reagent you use for saponification reaction, to push the reaction to the left, right? So, nope. Third, I can also increase one of the starting material. One of the starting materials. Question, would it work if I create the ratio of both materials? What if I double the amount of both reagents? The equilibrium will remain the same because you doubled both at the same time. However, if you only increase the ratio of acetic acid, then more of the ethanol will be consumed, right? Which will move the reaction towards the right to the formation of an ester. So you may only increase the ratio of one of the starting materials, not both. Last, we can reduce the amount of one of the products, either ester or water. Ester tend to have a lower boiling point because it doesn't contain any polar bond. Well, it doesn't contain some highly polarized bonding. For example, carboxylic acid and ethanol both have hydrogen bonding, which will increase the boiling point. And for ester, it doesn't have that issue, so the boiling point is comparatively lower. You may boil off ester so that the reaction can also move to the right. Third, let's talk about mechanism. To write a mechanism wasn't so hard for this reaction. However, there are so many things you need to pay attention to since the reaction happened in acidic environment. So be careful, do not write any intermediate that's very unlikely to be formed in an acidic environment. And we're gonna see many of the examples later when we're writing the equation. So we have acetic acid, ethanol. All right, so we have a nucleophile, we have an electrophile, right? As we said, for carbonyl bond, an oxygen will carry a partial negative charge, while carbon will carry a partial positive charge due to the difference in electronegativity of carbon and oxygen, right? So I will have the nucleophile to attack, and the electron pair being pushed and being carried by oxygen, what am I going to form? What do you think? Would they work out? Nope, you're forming an alkoxide, which is very unlikely to be existed in acidic environment, right? So I should rewrite. How am I going to rewrite then? There are two ways you can make the nucleophile to attack. And one of them is by protonate the carbonyl first, right? Since it's in acidic environment, it shouldn't be so hard to do. Oxygen plus OH. Well, then we can have the nucleophile to attack. Oxygen being pushed up, CH3, carbon OH, OH, oxygen, well, you had a neutral molecule to attack a positive charge, and in the end you should have oxygen carrying a positive charge as well, right? It also should, the charge should also balance. And well, we know the very final skeleton are right here, which means that you need to eliminate hydroxy somehow. However, before eliminate hydroxy, you need to deprotonate the intermediate. CH3, carbon, OH, OH, the rest will remain the same to make that a neutral molecule, right? At the same time, H3 plus. All right, then let's think about elimination, or how you can kick off the hydroxy group. Well, can I just kick it off? That shouldn't be so hard. I'm closer to my final step, right? I'm one step away. You will realize that you're actually kicking off hydroxy anion, which is very unlikely, again, in acidic environment. So let's go back and rewrite. This time, I'm gonna protonate first. Carbon OH, OH2 plus, CH2, CH3, and then I can kick off water, which is so much easier and possible in an acidic environment, right? All right, now, well, so I kicked off water, which is neutral, and I started with the intermediate carrying one positive charge. I'm missing something. There it is. There's my cation, right? It's a carbocation. The next thing will be make that carbon neutral. At the same time, at the same time, restore the, not restore, but to form the carbon-oxygen double bond, right? What am I gonna do next will be deprotonate the last intermediate and form the ester. And this is showing the whole process of how we complete a Fischer esterification mechanism. I also walked you through, all the small pitfalls that you may fall into. Be very careful what anions, what cations, what molecules you're creating, and whether that's a possibility in an acidic environment. Okay. And in the end, I'm not going to go over the detail, but I hope you will take a close look at the FTIR and proton NMR spectrum of the products, including analysis. And last but not the least, we know that esterification reaction and saponification reaction are, saponification reaction are reverse reactions, right? So start from an ester to acid and alcohol in saponification reaction. Since I already walked you through the mechanism for esterification reaction, do you know how to write an equation or mechanism for a saponification reaction? Think about it and write it out, right? The reaction will happen using sodium hydroxide as a catalyst, okay? And that's a question from me. And if you want to double check whether you got it correctly, you may send me an email with your mechanism. Alright, I'll see you in the next video.